Hyperbolic functions. Our objectives is to obtain general knowledge of hyperbolic functions, inverse hyperbolic functions, hyperbolic identities, and the derivatives of such functions. Certain combinations of exponential functions arise so often in mathematics that they deserve to be given special names. In many ways, these combinations are similar to trigonometric functions. Yet, no angle is ever involved. These combinations of exponential functions have the same relationship of a hyperbola. For this reason, they are called hyperbolic functions. Hyperbolic sine of x, hyperbolic cosine of x, hyperbolic tangent of x, and so on. The Gateway Arch in St. Louis was designed using a hyperbolic function. Let's dive into a little bit more detail of why they resemble trigonometric functions, yet they really have nothing to do with trigonometry. Recall that when you parameterize a circle with the parameter t, you get points on a curve that travels in a circular motion. And that circular motion is in the counterclockwise direction. For this reason, cosine of t and sine of t are referred as circular functions. When you parameterize a hyperbola with the parameter t, you get points on a curve that travels in a hyperbolic path, only on the right side. This point is going to be defined as the hyperbolic cosine function of t, comma, hyperbolic sine function of t. And when you evaluate this, it even gives you a hyperbolic identity. What is the definition of hyperbolic cosine and hyperbolic sine? Let's dive into the details. It is a combination of exponential functions. Not just any combination. It's such an interesting combination that the reciprocal functions, like you mimicked in trigonometry, also occur. Yet this has nothing to do with angles. This has everything to do with algebra and exponential functions. So if you have the hyperbolic cosine of x, we also have the reciprocal function called hyperbolic secant of x. And not a surprise, there's the reciprocal. We even have hyperbolic tangent of x, which is a ratio of hyperbolic sine over hyperbolic cosine of x. And if we have hyperbolic tangent, we certainly have the reciprocal function called hyperbolic cotangent of x. Here are a few pictures of such functions. Notice hyperbolic sine function is actually an odd function, or symmetric about the origin. The same with hyperbolic tangent of x. It's also an odd function, symmetric about the origin, and it also possesses two horizontal asymptotes. The hyperbolic cosine function is an even function, which means it's symmetric about the y-axis. You may have seen two telephone poles in your lifetime, and that wire hanging from two telephone poles is called a catenary, which is actually modeling a hyperbolic cosine function. You may have seen the ocean at some point in your life, and if you look at an idealized ocean wave, the velocity of such an ocean wave is defined to be a hyperbolic tangent function. So hyperbolic functions are probably around you and you don't even know that. Since hyperbolic functions are in terms of exponential functions, their derivatives are rather simple to derive. You just need your basic rules of differentiation, and these will arise. Now, if you find this confusing because of your trigonometry experience, you're not alone. Whenever you learn new practices or new rules, they might confuse you because of your intuition with prior practices. But with new practice and new reiterations, you will remember how to do these. And they're not too difficult to remember if you strategize. Note that the hyperbolic sine and hyperbolic tangent functions are one-to-one. That means their inverse functions will exist. And just like inverse trigonometric functions, you also have inverse hyperbolic functions. The hyperbolic cosine function, however, was not one-to-one. So you would need to restrict the domain of this function in order to get the inverse hyperbolic cosine function to appear. Since the hyperbolic functions were in terms of exponential functions, it's not surprising that the inverse functions are defined in terms of their natural logarithm. With the language of algebra, these are the inverse hyperbolic functions. Here are a few pictures of those inverse functions. Inverse hyperbolic sine is an odd function. Inverse hyperbolic tangent function is an odd function. Inverse hyperbolic cosine function is a very unique function with the domain value starting at 1 and moving towards positive infinity. Just like trigonometry, there are actually something called hyperbolic identities. Even though there's no angle involved, we still have patterns that are similar to trigonometry, yet they are not related. So here are some hyperbolic identities. The most famous one being the identity that coincides with a hyperbola. Once again, if you see this as confusion, make sure you practice using these identities in such a new context where you're able to remember the new patterns. We can also derive the derivative rules for the inverse hyperbolic functions. And we do this, like we did before, with implicit differentiation. And along the way, you might need some hyperbolic identities to help you realize that, oh, these inverse functions are really just functions of x. And once again, I repeat, there are no angles involved.